Hundreds of microservices sounds like a lot, but we are a little bit less than that. But yes, we still have the problem of autonomous transaction in the world of microservices. Thank you for joining, first of all, because there is other talk in parallel, so it means that you had to choose us somehow. So we are Nicola and Divya. We work in a team of 3 people along with Narayan. We had the luxury to mention the whole team because the team is small. And we work at Nexmo, the Vonage API. We work in a team that deals with services high availability, data migration, and data replication. So for all of those of you that don't know us, our mission at Nexmo, the Vonage API Platform, is to build a cloud-based communication platform to allow developers to interconnect their applications with the communication infrastructure. We kind of abstract all the problem of this integration. And in general, no matter if you're a single developer in his own room trying to make a POC, or if you're a big enterprise with few lines of code, send an API request, you can dispatch your traffic and provide your application with the capability to interact with all these different kind of communication tool globally, and without having the problem of deal with country-specific regulation, local carriers, which I can tell you it's a big burden. Yeah, so cloud platform, communication platform as a services are ubiquitous these days. So yeah, maybe, who knows, you are already using us somehow and you don't even know. Something about the agenda. Today we are gonna a little bit talk about the fairy tales of how we ended up having, started with a small backend application, we ended up in a monolith. Then how we tried to scale this application, which was basically a read-intensive application. So how we scaled our read workload with the internal tool that we have developed called Volga. Then that supported us also for the migration to microservices. And then when we were in the world of microservices and we thought that the worst was passed, we had the problem of transactions there. And we are gonna try to talk about our strategy to fix this problem. Yeah, so there you go. We have once upon a time our small backend application. I believe from an engineering, software engineering, distributed engineering standpoint, this is perfect place to be. You can easily delegate consistency and isolation problems to your MySQL engine. Of course, this is a fairy tale, so I'm not adding into this diagram proxies, cluster replication for disaster recovery, and high availability, all this stuff. It's just front-end application calling a back-end application with a database. Yeah, so as I've already mentioned, we are talking about a read-intensive application backed by a MySQL database, MySQL. Yeah, so the company started to grew across region as well. So at some point in other data center, we had other application interacting with this backend application that was not anymore tiny, but it was evolving into a monolith. And we reached this point where it was time to deal with the scalability. And the main problem were read workload, as I already have mentioned, and the monolithic architecture. So let's see how do we try to solve the problem of read workload. And the problem can be decomposed in 2 problems. There is too much load on that backend database, which is, again, putting in jeopardy the availability of the right traffic from that, on that data store. And of course, there is the problem of latency for the application that are in the other data center, above all, that are doing this network hop to reach the primary data store. Yeah, so the solution are the common solution. We add in caches. We try to spin up read in sync replica in other region. And that's where CAP Theorem comes into the game, because of course, this is kind of to set up a little bit the expectation to say, guys, there is no way you can have at the same time in a distributed application high availability, high consistency, and partition tolerant. partition tolerance, being resilient to network failure. But actually, we cannot avoid in real world to deal with the network failure because networks are unreliable. So the choice is between two of the triangle, and it's between consistency and availability. Basically, you have to choose when you have a network partition, if you want to send back to your application a 500 or an inconsistent view of the data. And yeah, the first real choice here in that trade-off is basically when you're adding these caches around. And the problem is, how do you notify this caching for updates or cache invalidation? How do you send cache invalidation notification? And that's where the quote from Phil Carlton start jumping into your mind, that there are only two hard things in computer science, cache invalidation and naming things. And you start understanding why cache invalidation was such a problem. And there is kind of an anti-pattern that I've seen very often happening, and there is this problem of dual writes, where basically to notify your cache from your you manage these updates from your application. So basically, the application in parallel writes to the primary data store and then write to a message queue or to whatever other technology you have available to dispatch changes to the caches. But this problem of dual writes has two main problems, and it's that without a complex coordination protocol, like for example two-phase commit, it's very difficult for us to guarantee that the two writes are consistent, and the ordering of the change wherever your application needs this requirement, your cache needs this requirement is maintained. And also there is another problem that the logic to write to the messaging system is strictly coupled with your application. That means that once you want, in the future, when you want to refactor that backend monolith and maybe decompose and segregate it into microservices, yeah, this is gonna be kicking you. It's a problem that you're only postponing. So there is actually a pattern for solving this issue. There are several patterns actually, but the one that we went for was log mining. Log mining means that you basically take your primary data store as the source of truth. You extract change from its transaction log, and with the I'm sure you're aware that with MySQL we have this log of transaction available. And therefore, we connect directly to it. So we try to create a sequence instead of writing in parallel to the two sides. So we connect as a replication slave to this source of truth. We stream the changes through Kafka. And then on the other side, we apply the changes to caches. And also, why not? Since we are there, we also use this solution for replicating, creating in-sync replica of the primary data store in the other data center. This is exactly the way MySQL does replication, if you are familiar with it. And so our design evolved in something like this. Now we don't have anymore the problem of dual writes. Plus, we also got something more out of it. Once the changes are there floating in this highway that we have built, it's very easy for us to create materialized views of our data from our primary data store into other data stores. We can use it to push changes to secondary index, exchanging data with other teams by sending data to analytic platform. Again, we can send them to different caches in sync replica that are homogeneous and heterogeneous. So this is a great tool to support also migration, as we will see afterwards. But yes, I mentioned cap theorem before, and there was something we had to give up. And this was for respect to the scenario where we were on the single data store, we had to give up that kind of capability to delegate consistency and isolation to the data store into a new consistency model, which was sequential consistency, which, if you're not familiar, it's just one of the paradigm of eventual consistency, where you are also adding the constraint of dispatching the changes in order to your other end of your eventual consistency stream. In this case, we were able to achieve this leveraging, of course, the intrinsic ordering within the binlog file and using Kafka in order delivery. And the other thing that we have to give up is like there was a relaxed semantic, because of course in order to achieve reliable delivery, we have to pay the cost of some time or redispatching some messages. For example, if one of the two stages of our pipeline goes down, source of sync, as I have mentioned before, goes down, when we bring these stages up, we could dispatch again some of the messages. Yeah, other feature that we have embedded within Volga were snapshotting of, we are creating views of the data also and store somewhere, so that if we have a disaster, we can recover the state of our application. We can bootstrap in sync replica and slave very quick through our snapshots. And also we use this snapshot for correctness. So periodically we check that the snapshot that at a given offset is equal at this old destination and the source. Also, there is another important thing, is that once your data are in this highway, you are able to collect a metric about the right access pattern, which is very important tool, again, to support the migration afterward and the segregation into microservices. We are also, for respect to other tools that do the same thing, we are also supporting different level of partitioning. Because since this tool was mainly starting the designing not as a change data capture, but was mainly designed for replication. Yeah, we added the problem of like having a partition level that was around the transaction, and then we are using homomorphic caching for integrity checks to check that the correctness of the transaction online is respected. Yeah, so we solved the problem of the reads. And then we have the drawback on the monolith. I go very fast on this. It's a big problem that we have already seen around, but there was some specific issue that we have in our organization. In particular, we had the incapacity to scale business domain independently, and barrier to innovation. Even just a simple task of upgrading a library in that monolith was becoming a painful, gargantuan operation involving a team, inter-team negotiation. And yeah, difficult coordination then, also because it was very difficult for us to understand this and segregate the scope of ownership of different teams within that code base. So all this was creating just very bad mood of developers to work on that code base, and barrier to innovation also for product, from the product side. That product was really scared to go to our developer and ask for new features because of the bad mood. Yeah, so it was time to migrate to microservices. Here again, another pattern that is very common in this migration. I don't know if you're familiar with the Strangle pattern. By the way, how many of you guys are dealing with monolith at the moment? I'm very curious to do this small survey. Is any of you also in this phase of migration to microservices? Okay. So yeah, Strangle pattern is like a very common solution. It's a pattern that evolves basically in three phases. In the first phase, you try to build like an application in parallel to your existing logic. Then for some time, you keep these two reality living at the same time, and then at the end, you cut off, you strangle the old application. This is very common. There is like this analogy with these fig trees that since they are in this very dark forest, they have to leverage lighting from the mother tree, so they basically start blossoming their seed from the top of this tree, and then they goes down, creating this wonderful natural architecture, but then the host also is strangled, so they kind of destroy it for their survival. Nature is amazing. Strangle pattern, yes. So I talked about the first phase of transformation where we are building the first app. In this phase, we really deal with all the problems that are strictly related to the app. We build the deployment pipelines. We start creating a test pre-prod environments. We set up all the monitoring tools that we are going to need for the live food of this microservice. But all the traffic this goes on the other side into all the monolith. Then there is very painful phase, which is the migration of the dependency to the new API. Of course, I didn't mention in the back end, the new API is still going through the monolith. So, and this is a very painful migration because this is where the migration becomes also social. You have to go to the different team, advocate the new API, push them to migrate as soon as possible, start deprecating the API in the old monolith, and yeah, maybe support them in bringing your new dependency into their tests environments. And now you start having this problem into our mind. How am I going to migrate then the real problem that is the data under the hood? And that's where another famous pattern comes to your mind is the common query responsibility segregation. So basically, the read model into your application is completely decoupled from the right models. And to achieve this again, we go back to the previous conversation about consistency. You cannot achieve this by keeping the strictly consistency between the write store and the read store. So, yeah, this is very, very good because with this pattern, you can start migrating your read workload and in parallel, still keeping the source of truth in your main database so that you can also make incremental the migration of the data from your data store, which is the most sensitive piece of your migration. And yes, the benefit of common query responsibility segregation are a lot. I added it at the end the support for incremental migration, but of course, you can create a read model that are optimized for your queries that are completely, that can scale independently for respect to your write model. You can of course create separation of concern, which is always good in our work. You can improve security because then it's very easy for you to decouple security policy for write model and read model. And yes, you can basically start the loose coupling between your data store in the backend. So basically, you reach something like this at some point. And this is exactly the second phase. The Coexist phase has definitely started now. Then, in our case, we got rid of the monolith incrementally by migrating the business logic of the monolith into our new application. And that's when basically you can start getting rid of that dependency. For us now in this phase, we can mark the migration as completed, but then there is still the write traffic that is going to that other data store. And that's when the metrics that we had collected before with Volga come into the game, because then depending on the right access pattern to your data store, you can define different strategy to migrate this data. You can also decide not to migrate the data because the data are fine there. It's up to you. You could also decide to accept a small downtime and decide where to go with the downtime, because now you have graph of distribution of request on your master. So yeah, finally you get rid of the monolith, and I guess you guys get rid also me, because I'm gonna hand over to Divya.
Hello. Yeah. So yeah, so we have solved a lot of problems till now, but let's go back to the basic topic of the presentation. So we said that, hey, we'll talk about transaction and how do you handle all these things, consistency, isolation, and everything. So Can someone tell me what is an autonomous transaction? How do you define an autonomous transaction and how that definition is important in the context of transactions? Anyone? No. Okay. So if I start with an autonomous transaction, so autonomous transaction is that, let's say you have a transaction that in which you are doing multiple things. You are doing, let's say, some insertion, updates, and whatever operations. So the system divides your transaction into different parts. So now a transaction is being divided into transaction 1, transaction 2, transaction 3. Now you apply these transactions, you get the result, and you pass on this result to the actual transaction, and that will be your final result. So an autonomous transaction is nothing but a division of your request, and then completing each of them one by one, and then finally giving back to the actual request. So, and based on this definition, there are different patterns which came into picture. For example, whenever you go in a distributed system and you perform two-phase commit or any other thing, you see that. So now let's come back to this monolith application. So there are a lot of problems with monoliths, I agree, but there are some good things about it, and this is one of them. So when you have, let's start with an example. So let's say you work in Uber, and the simplest thing you do is like, okay, you have a booking, you have a driver, and whenever you do a booking, you mark the driver as busy, and you mark the booking as allotted. So, and this is very like a simple application. So you just, if you have single database, you just say, hey, begin this transaction, do these two things, and end this transaction. Now, at this point, your database will make sure that this transaction is either succeeds or fails. There won't be any transient states in between. There won't be any inconsistent states in between which you need to handle. Everything is taken care of by your database engine. So now you decide that, hey, we want to do fast delivery. We want to add new features. You move to this new place where you divided your monolith application into multiple microservices, and each one is backed by the database, and you design your domains in a way that, okay, we don't need to solve this problem. I don't need to do the transactions within the microservices. So that means that you don't need this entire thing. So let's say now you have a driver service, you have a booking service, but you made these in a way that the domain are not as separated. But let's say tomorrow your product is coming and asking you that, hey, we have this feature 1, we have this feature 2, let's start this feature 3, which can do the feature 1 and feature 2 together. And you're like, yeah, we can do that, but I think it's not that straightforward, because then if you create this different service, then now you have to deal with transient state, you have to think about the consistency levels. Okay, how do you handle the eventual consistency between services? What will be your isolation level? How would you roll back your transactions? So because if you are using, let's say, MySQL or something, if a transaction fails, it will automatically roll back the whichever succeeded. So now you have a new set of problems to deal with. So one way or other, at some point of time, you might come into a scenario where you have to deal with this problem. So now obviously this is not a new problem, and there are many companies out there who have already solved it. So what are the possible solutions of it? So this is what we could look on the internet. So there are very two standard approaches of solving the transaction. One is two-phase commit, and so this two-phase commit is not this is the distributed two-phase commit and the Sagas. So how many of you have already heard of Saga pattern and coordinators, and how do you deal with it? Okay, nice. So I think so for the rest of you, I'll explain what is Saga pattern, what is two-phase commit, and I'll also discuss that what is this. We also have some approach which is basically in the middle of both of these. So let's start with two-phase commit. So now this is the diagram of two-phase commit. So let's start with very simple example. Again, we have this driver database and the booking database and the coordinator. Now when you do a distributed two-phase commit, you need some coordinator to coordinate the entire transaction, to roll back and to handle all these consistency of yours. So you start the transaction. Now as it suggests, there are two phases of it. So we start in the prepare phase. So your request goes to the prepare phase, and when the coordinator asks that, hey, this transaction started between this driver and booking, So these two databases will look at the request. They'll say, hey, yeah, I can make this change. I have enough resources to do. OK, this change, this is the redo log of this change. So just in case if later I have to roll back. And also, it will log the tables. So because now here I'm talking about that we should have the strict consistency. So that means if you do not log the tables, people will be able to read the uncommitted data. What if the later transaction fails and you have to roll back? So we don't want to go into that scenario. So you log the tables, and then your database says that, hey, it's prepared, and then you send a commit request. And if, let's say, everything goes well, you committed, your data is committed, and if just in case, if any of the commit request fails or any of the prepare phase fails, then it will just use the redo log to roll back the transaction if it is committed or made some changes already. But it's a good approach. You get a lot of benefits of it. But the only problem is that during this entire time, your database tables or rows are logged. So which makes this particular approach slower and not very useful in the current state of architectures where we have so much of latency, so much of throughput of the requests. So, and another problem is the deadlock. Now, what is the deadlock problem? So in a transaction, when you are doing these two things, or there are like, let's say you log two tables, and there is another concurrent transaction which also want to make changes in the same tables. So there is a possibility that you can go in a deadlock scenario where these two transactions are waiting for each other to unlock the tables. Now you also need to think, okay, how do you avoid this deadlock? How do you, maybe if there is a deadlock, then how do you solve these problems? So, but good part is that, yes, you get a strong consistency, you get read-write isolation, so all these things are good. So then this, as this was slow and people needed a bit faster things, obviously there are some tweaks you can do on two-phase commit, which we will discuss later in the same presentation. Let's move to the next one, which is like Sagas. So now let's start again the same. Now there is a subtle difference between the two-phase commit and Sagas. Can anyone tell me what is this diagram? And we had the exactly similar diagram in two-phase commit. So if you look at here, it's if you look at the two-phase commit, it was not the application, it was the database. And in Sagas, you have the application. So the one fundamental difference is that Sagas happen at the application level. That means that the compensation or the redo log, which you are using in two-phase commit to revert or to roll back your transaction, in Sagas, your application has to support that. Your application, it's like an apology protocol. Hey, we wanted to be in this state, but we are not in this state. So later you go to customer and apologize, oh, sorry, we can't make your booking, or something like that. So it more like it works in that way. So now again, we start with the same thing. So you start a transaction with the coordinator, and you don't prepare or anything. You just say that, hey, I'll make this change in. If everything goes well, then I don't need to worry. But what happens when something fails? So let's say if everything goes well, I don't need to worry. But when this particular request failed, then what you do, you send the compensation that, hey, sorry, we made this booking, but we had to cancel it because we kind of overbooked or somewhat like that. And then you apologize and you are done. So that's what you do with Sagas. And when the compensation is success, you end the transaction. Now, the good thing is that you don't do any locking or anything on your database. So you are allowed to read the data which is not yet committed or which might be rolled back eventually. So now what are the problems with this thing? So the good thing is that, yes, you don't have logs. You have long-lived transaction. You can add multiple services. So you can add any services to the coordinator and start the transaction between them, and it will wait to, the protocol will make sure that your system comes into an eventual consistent state. So those are the good things. And obviously, you don't have any tight coupling between services. So every services can be implemented on their own, but they need to have few things. So now, the few things is that first, your isolation is relaxed. It's very difficult to isolate the concurrent transactions. Now, another thing is that your application now has to support this compensation logic, which means that, let's say you have an existing infrastructure of microservices, and now you go to every microservice and you go to every microservice and add that, hey, if this request happened, this is how we compensate it. If we did one booking, we will basically cancel this booking and give this coupon to the customer. Sorry. So yeah, another one big problem is that now here you are basically allowing the user to read a data which might be rolled back eventually. So that means, so if you go back to the same example, you made a booking in Uber, your driver and booking, so you need to mark your driver as busy, your booking has to be allocated. So the first thing which happened is your booking application gets the request, it marks the booking as allocated, but the driver is not busy yet. So that thing is still in process. At the same time, another concurrent transaction comes into picture. He says that, hey, give me all the free drivers available. So now as the driver is not busy, your database will give, oh, this driver is free. And it will allocate the same booking to the same driver. Now what happens here that there is one driver who gets 2 bookings, so one booking he has to cancel because he can't complete 2 bookings at the same time. There is one eligible driver who could not get the booking at all because we've had the problem of dual bookings, and I've seen this problem of having dual bookings or bad experiences with the customers due to all these things. So now, how do you solve this problem? So this is good thing. For example, a lot of companies already have these things in place that, hey, sometimes you overbook due to these reasons, and then you eventually compensate. But we could not do this because, let's say, there is one more bad thing is that you can't use this if you have some banking transaction. So for example, let's say you have a credit and you have a debit. Now you can always credit in someone's account, but you can't debit without their consent. So that means that there is no way you can compensate this. So what if the kind of application you have does not support the compensation? So then it again becomes very difficult to use this, and you are then the only way you can do is two-phase commit. So we were kind of in a similar situation that this was very difficult for us to use. So we were just thinking, what else we can do? Is there any way that we can kind of make sure that the user never reads this uncommitted data? Can we tweak these protocols to come to a middle ground? So we read a lot of papers, and there is this Dropbox paper on Edge Store. So it talks about how they had similar problems and how did they solve it. So based on that, we also kind of designed a similar thing. So it's not new, it's just if you go out on the internet, you search for it, there are many places you can find similar thing, but we call it Shadow. So it's a distributed two-phase commit. Now, let's see how we go about it. So again, we start with the same place where we were in Sagas. So you again have a coordinator, you have the driver application, and you have the bookings application. Now we introduce one more unit here, which is called business logic unit. So what is business logic unit? The business logic unit is basically we want to decouple the business logic from the actual transaction. So this means that, for example, if you have to compensate, or let's say you have to roll back, all these things can be put into business logic unit, and your coordinator can perform independently from that. So if, let's say, tomorrow you want to add some application, delete some application, your coordinator or internal things doesn't have to change. So that was the reason. Now, also this unit, it doesn't have to be a separate service or something. It can be just a library, or which you can maybe sidecar with the coordinator. So now the request, you get the request. So it comes to the business logic unit. Now the business logic unit is aware that, hey, there are these 2 applications, and the transaction will start between these 2 applications. So the first thing it does is, it will go to the coordinator, and it will ask for the transaction ID. Now, this transaction ID is the key of the entire transaction. So every time you want to know any detail about this transaction, you can get with the transaction ID. That is one. The second thing is that the coordinator is the one who is always aware that what are the current ongoing transactions, what are the transactions which are in process, because the first step in the transaction starts from the coordinator. So you take this transaction ID, and then you said that, hey, you go to the driver and bookings app and say, hey, there is this transaction which needs to be done between drivers and bookings. So can you do this, can you fulfill this request? So now the driver application is obviously, it's your already built microservice application, and what our goal was that we don't want to change in any of the microservices. If there is a possible way to do that, we don't want to go to every team and tell them, hey, can you start this compensation? Can you support this for us? Can you support that for us? So how do you do that? So we introduced the Shadow. Now what is Shadow? So Shadow is basically a table which is exactly same, or the schema is same as the actual table. So actual table is actually where your data gets inserted, and shadow table is basically kind of the prepare phase of the two-phase commit. So what is the purpose of the prepare phase in two-phase commit? You want to save the data that, hey, these are the changes which will happen eventually. And also you don't want your user to see this data. But if your user is reading from the actual table, and if you put this data in the actual table, he will read it from there, and then it will be difficult for you to handle this. So instead of putting it to the actual table, you put it to the shadow table. So exactly the same data, you put into the shadow table, you add extra column with transaction ID and timestamp. Now the data will go into shadow table. Now what is shadow client? So now obviously, as we said, that we did not want to make much changes in the application. So this client will basically, the request will come to your driver application, then it will use the shadow client, and shadow client will make the changes, all the changes. So for example, if we had, hey, mark this driver as busy in this table, shadow client will change that, mark this driver as busy for the table, for the shadow table of this actual table. So it will change this, and then finally the data will go to the shadow table. So now what happened here? So now you have the data available with your system, and now if I say that, let's say that your transaction is success, and later at some point of time, I'll make sure that the data goes to the actual table eventually for you. But now how do you read this data? How do you know that when it will get committed? How do you know that how do the user will get that if it succeeds or failed? So we had this one more unit, everyone is aware what is Volga. We already had this thing in our previous slides. So the purpose of Volga is that it can take the data, it's like the bin log mining. So it will read from the bin log of the shadow table. So, and then it will put them into this Kafka. So we already had this Kafka cluster across. So we'll put it into Kafka in a specific topic that, hey, there is this transaction which was running, and this is now in this topic. And the coordinator will be reading from the same topic. So now, as I already told you, that coordinator is the one who gave the initial transaction ID. So that means it keeps it that, hey, there is this transaction started few milliseconds ago or few seconds ago based on your latency, and this was still in process state. So the coordinator gets these two requests, these two events from the Kafka, and when the coordinator get these two events, now it knows that, hey, this transaction, it gets the event, that means that the transaction data is available in the shadow table. And at that point of time, you just mark it commit, that, okay, we got the data, we successfully done with your request, and we mark it as commit. And it will put back this event into Kafka, that, hey, this transaction is committed, take it, do whatever shit you want to do, and the job of the coordinator and business logic unit is done here. And your user gets that, hey, this transaction you did, this booking you did, and you were successfully able to do it. Now, how does it actually move to the actual table? Is basically now mark transaction as complete, and then again, the Volga will read back this event from Kafka, and it will go to the shadow table and mark this transaction as complete. So now the transaction is complete. Now the only thing you need to worry about, how do you make the user to read this data such that you always make sure that user reads the committed data. So it goes to the shadow table, marks. So there is one more component to this which we haven't added in the slides, but it's like more an asynchronous application or library or maybe job or whatever you say it, but it's more like it will go to the shadow table, it will read from the shadow table that what are the transactions which are in complete state and move to the actual table. So that means that eventually, as we previously said, that eventually we will make sure that your data is available in the actual table, and we'll keep removing the data from shadow table. So at any point of time, the shadow table will have some transactions which are in processing state, some transactions which are in complete state, and that will be the state of the shadow table. So now, let's see, how do you handle reads? How do you define that we have a consistent read? So just to simplify this diagram, so again, you start with the booking app. You have the shadow client, you have the coordinator, and you have your database. So the request comes to this application, hey, can you give me this booking with the ID 1? So the first thing, we have the shadow client. So the booking app will send it to shadow client that, hey, there is this request to read this data. So what shadow client will do is, it will go to the coordinator and it will ask, hey, what was the last committed ID you had? And now coordinator is aware that, hey, this was the last committed ID I had. And that means that before this committed ID, all the IDs are committed or failed, or they're not in some transient state, or they're not in between. They have a final status already before this committed ID. So shadow clients gets this committed ID, and what it does few things. So now what it first do is, okay, this was my committed ID, this is the read request, okay, so it will do a query, okay, give me all the read request, let's say which has with ID is equals to 1 or ID less than equal to 1 or whatever is your where clause. So it will get this data from both the actual table and shadow table, then it will join that data, and then it will filter based on the last committed ID. So that means that now it has to get the data from the actual and shadow table, because there might be a point where your data is not yet in the actual table. It is still in shadow. We are still in the process of moving it to the actual table. So you have to read from both, so that you make sure that your data is being read, and even as soon as you send the success status to the user, then it will union the result. You have to do it in order to get the final result, and it will filter. So filtering will make sure that you don't read anything which are still in processing state. So the filtering will make sure that just read the transactions which are which completely success, and that's how it will get this data and finally return to the user. So now in this way you make sure that you always read the committed data. So now this cannot happen that if there is a driver or there is a transaction which are still ongoing, it will never read that, or it will wait until the transaction is complete if this write request happened before any read. So now the question becomes, what are the good things about it? You have a slower reads. That's true, because you might say that maybe when we do the join operation and filtering, it will take a lot of time, but that's not true, because your shadow table is always small, as we are continuously moving the data from shadow table. So it will mostly have the ongoing transaction most of the time. It's complex to implement, reason being that you now have to implement this coordinator, the business logic unit, you have to implement this different client, you need to have this either this Kafka pipeline in place already. So those are there are many components to it. Good part is that you don't lock anything. So your protocol makes sure that you always get the committed or consistent data. You get the read committed isolation, you get the read committed consistency levels. So now, this is the comparison between the two-phase commit, Sagas, and shadows. So the consistency in two-phase commit, here we are discussing about when you lock everything. So it will be linearizable. In Sagas, you get eventually, it will come to a consistent state. Shadows, it provides you read committed. When we talk about isolation levels, two-phase commit is serializable, yes, because we are locking everything. We are not allowing two transactions to interfere with each other. Sagas is mostly relaxed isolation. Obviously, you can maybe, I'm not sure if you can change some implementation and make sure that, okay, somehow if you go to a good or better isolation levels, but shadows will make sure that you always get the read committed isolation levels. Now, what to use? It's very difficult question to answer that which protocol might be a good fit for your system. So there are so many factors to it. You know, you need to know that what is the consistency levels you want to, what is the consistency levels you want to have in your system, what is the isolation level you need, what is the latency and throughput of your system. If maybe you can, it's okay for you to have some latency, you don't have that much of throughput, but you want very strong consistency and serializable isolation, so then maybe a two-phase commit can be better fit for you. It depends what you can compromise with. As we know that in CAP theorem, partition tolerance will always be there. So you have to choose one between the consistency or high availability. So what is more important to you and where you do the trade-offs. So I think based on all these factors, and if you know that, okay, these are my requirements, so I think if you are perfectly aware of all of these, then you can choose a protocol, whatever suits your needs. So that's all from our side. Thank you.
Thanks. Could you please show the slide regarding the microservice migration, when the monolith and microservices work in parallel with MySQL database. Yes. Yeah. This one. Or even previous one. Yeah, this one. Yes. Yeah, this one. The question, how the write operations are working in this case. So imagine we have two tables, driver and bookings. Yeah? So monolith will write something in this table. How the microservices doing? So they have own copy of the table and you somehow synchronize the data, or it's use other instance of the database, or write data in the same table. This is not quite clear for me.
Yes. Okay, sorry for the lack of clarity, first of all. The idea is that, of course, as you're pointing out, you don't want to handle your write traffic into different points, because then you have a problem of merging this state which is updated into different sites. So the catch here is that in this phase, in the back end of your microservices, you still are querying the right API from the old monolith. So basically, still the path of the request comes into your microservices, but then it's dispatched in your monolith. Like this, you don't have to have this problem, because the write goes only. There is only one source of truth for write. There is no way we can handle without like a conflict resolution algorithm. There is no way we can handle.
In this case, you need to have two implementations. One implementation microservices that talk to the monolith API.
Yes.
And the second one, you have direct persistence level, so you have kind of second migration then.
Yes, that's why the migration is incremental. In this phase, the microservice is still a very thin layer, which is already handling maybe. So if your question is about if I have to add the new API, where am I going to add that? That's yes. You can still have. This was a simplified model here. Of course, the other purpose of the microservices, which is already there, is not to prevent new feature to come in and being served, but it's you don't want at the same time to go and implement this feature in this monolith that you want to touch as little as possible. So yes, you're right. If you already have a strategy of a new write model that you want to implement in the future, yes, there would be another database there with your write model. Of course, this prevents you to do relational operation like foreign keys, updates, and yes, exactly. So for that, that's when the transactions start coming into place. You have to have like sort of coordination protocol that allows you to write into different places in a lockstep. That write migration becomes very complicated. So for us, the approach that we used the most often was to keep the data in the old write model, and keep using the new model only for reading. That was the approach that for the business critical application we took in place, because for us the real deal was there to get rid of that big monolith from the dependency path. More than the data model itself in MySQL. But yeah, there were teams that were dealing with the problem of writing the migrating the write model in parallel, and for those they created very complicated tool to migrate accounts performing this migration on a per accounts basis. Yes, but this was like just a simplified version of this migration. Of course, I didn't go into the details of how to migrate the write model. I agree with you. It's very complicated problem to solve. Yeah.
I have a question about the Volga thing. Is that open source, first of all? And thanks. My question was, is Volga open source, and is this something we can all use? And second, when it replicates bin logs, does it support replicating just statement bin logs, or do you have to replicate the entire row record?
Currently, Volga is not open source. There are a bunch of projects that do log mining with different strategy. For example, I see there is a tool by Red Hat called the Bisium. There is plenty of tools that have the same thing. The Bisium does something a little bit different than us. It's tailored for change data capture. We tailored Volga to support in sync replica. So About the row-based statement. So we use row-based replication under the hood. And reason being is that actually we don't want to incur in this issue when we replicate, for example, foreign keys or transactions. The tool, yes, tool currently, sorry, I didn't answer the previous question. The tool currently is not open source. We're working on it. Let's see if we handle the bureaucracy within the company to do that. Probably follow us. We'll keep you updated. Thank you.
Thanks for the presentation. I think you made a very good, let's say, overview of how hard it is to keep consistency in distributed systems. With the Sagas implementation, I see that you are becoming even more distributed, okay? Because you are adding shadow tables, you are adding Kafka. So if I think in a recovery scenario, for instance, you need to take a backup, and then you need to restore it, then, I mean, everything is even less clear, okay? Because you have the shadow tables, you have some state in the Kafka. So I don't know if you if you can comment something about that, or how to solve that disaster recovery in this implementation.
So we kind of haven't done that, so the disaster recovery thing. So right now, I think as we are using Volga to basically replicate the data. So we don't really, what you can do is basically when you replicate the actual table, so the snapshot are like timed snapshots. So at any point of time, you take the entire backup of your database, and then what we are doing right now, we are currently in the implementation of this checkpointing thing. So what we do is, we keep this data in the RocksDB in the local machine, and then after every 5 minutes, we upload this entire RocksDB to AWS, and then from AWS, you can create a MyRocks instance, and then which you can use just in case if something fails. So that's what we are trying to do. That is still in progress, so it will be very difficult that how it will turn out, but I think we did some tests with it, and it should be doable, but right now we don't have that in place yet. It's still in progress.
So I want to comment also. So these are not this is not an algorithm that we invented, let's say. This is a well-known strategy that a lot of companies using. I can mention some product. There is the previous called Fastcar in Alibaba, now becoming a SATA project. There is Edge Store for use the Dropbox for cross-sharding commits. So there is a lot of tools that are going into this direction. There should be a parallel triangle, in my opinion, for respect to the CAP theorem that has other 3 dimensions. That is complexity, latency. I mean, you have to mention other stuff into the game. Of course, for a small presentation like this, the CAP theorem is a very useful tool to explain the trade-off. Yes, it's very complex, but if you want to gain that consistency step and that isolation step, you really have to manage this complexity, or you have to pay the cost of latency for the two-phase commit. But yes, these are very complex problems, and that's why databases or product that solve this problem for us and nowadays are getting so popular. I see the Amazon, the cloud, all the ecosystem of the cloud data stores that are solving this problem for us. So because it's not everything can afford to invest money in solving this issue. So yeah.
Yeah, I think if we manage to come again next year, maybe we'll be able to give you better statistics on the performance and data recovery and on everything. But right now the work is still in progress, so we don't really have that yet.
Thank you.
Oh no, I think he had a question.
Could you switch to the slide with distributed two-phase commit?
Which one?
Distributed two-phase.
Oh, the distributed two-phase commit.
Yeah.
This one?
Okay, that's fine. So the way I understand this is that in the microservice world, everything strongly relies on coordinator. So what happens if the coordinator fails? Because the way I see it, if coordinator fails, then basically the whole system fails.
So the coordinator, so first of all, it's not, so the coordinator is like, think about it, it's a very small application which just keeps the transaction data. So what you do is basically, after every some time period, first you have multiple instances of it, so which can reduce the failure scenario. Second, we try to make it as stateless as possible, so you keep the checkpoints in your database that this is in ongoing and this is what currently having. So what happens if the coordinator goes down? If there is a transaction which are already committed, it won't affect that, but it will affect the ongoing transactions. So whatever transactions will be in ongoing, there will always be a timeout on those transactions. So in worst case scenario, if all the instances goes down and you are not able to collect your data, there is a possibility that some of the ongoing transactions will fail. But eventually when it will come back, it will read the state and it will start from the state where it went down.
So the thing that Divya has forgot to mention is that the coordinator itself is an high available application. So and again, this is another problem that is very common. I don't know, for example, if you have ever run into a software tool called Orchestrator that MySQL, that GitHub used for high availability of their MySQL data master. Whenever you have like a tool that does coordination, as you say, it becomes very easily a single point of failure. So that application must be itself being designed to be highly available. So there is different instance of this guy going in parallel, working in parallel. If, as Divya was saying, we didn't want to have a coordination protocol within the coordinator. So if you lose the coordinator while the transaction is ongoing, you lose the state of that transaction, but the other transactions are served by other applications that are running in parallel. If this was your question, but yes. If at the moment to reduce the complexity of that piece of code, we didn't want to be highly do something about the state of the online transaction which is in progress. So we failed the transaction. If this was your question, I don't know if this.
So I think how the transaction fails is, let's say at any point of time you are not able to send this data to Kafka, or let's say the final commit did not happen. So then every transaction will have a timeout of your system. For example, let's say if the transaction does not go in a committed state after, let's say 1 second, then we'll just fail the transaction. Because it also, if we do not fail the transaction, then we will also create a problem with the concurrent transaction when reads and writes are happening at the same time. So in order to solve that, we just fail the transaction so that the user can retry the transaction instead of going in an inconsistent state for the entire system.
And what you are saying is that this strategy or approach never is used by AWS and other public.
Sorry?
And what you are saying is that this strategy approach or whatever is used by AWS or other?
No, not AWS. It is being used by, the Edge store, which is by Dropbox, it is being used by Fesker, which is from Alibaba. So they do a similar thing. So what we did is basically they have this entire store, which internally does this thing. We just kind of destructurize it, separated out the component, and use the same strategy at the application level. So if you go there, then you can actually read the same protocol. That's how they are managing this consistency and isolations for their application. So they have an entire database or entire store for that. We don't have the entire thing. We are just using different components to get the similar results.
I not really get this shadow client stuff. Is the shadow client above the drivers app? So every request to the drivers app goes through the shadow client,
no, it's
or it's
like,
behind?
Yeah, so for example, in your Java application, you have the MySQL client, or you have, let's say, your JDBC client. So the shadow client is exactly similar. It will support all the MySQL requests. It will just tweak the request based on the protocol. So you, instead of using it as a separate client or library, you just change your MySQL client. So if there is any transaction, the shadow client will make the changes. If there is nothing, it will work as it is and let your request go through.
So the shadow client injects it into the
Yeah, it's
drivers.
kind of a
Okay.
library.
Cool, thanks. Also, in the next, probably it was some of the next slides, you said last committed transaction.
Oh.
Does that mean that the transaction should be committed in order?
Yes, transaction should be committed in order. So it depends on the coordinator. So what coordinator does is basically this transaction ID, technically this transaction ID should be an incremental thing. So let's say a timestamp. So let's say you get a 2 concurrent request, and if your concurrent request, you have a read and write at the same time. Now, you will only face the problem when the reads and writes are happening on the same key, not on different keys. So if they are on different key, it doesn't matter. But if they are on the same key, so let's say the coordinator gave a number to the write transaction. Let's say the coordinator gave a timestamp to write transaction is 5 and the read transaction is 6. So in the read committed isolation, we have to make sure that this read 6 should read the write 5 as well. So in order to make sure, that's why we have this timeout thing. So if you read about the Google spanner, it also have the 7 milliseconds of gap between every transaction. That means that every transaction should complete within this time period, and if it does not complete within this time period, we will fail it, because then there is no way you can deal with concurrent transaction. So it has to be incremental, and so the read transaction will say what was the last committed ID. So for example, my ID is 6, the ID of the read is 6, that means I should be able to read everything before this. And if there is anything in the waiting state during that period, that if there is any transaction which is still ongoing, the read will wait until the transaction is complete. And if the transaction is not complete within that time frame, which you can decide based on your latency of the system, then your read has to fail, because otherwise then you will go in trouble. For example, instead of read, what if it's on other way around, like you first read and then you write, then it's okay, because your write is happening after the read. So that's how we are making sure that you get the read committed isolation level.
So basically serializing the transactions?
Yes, basically serializing the transaction, yes.
Okay, thanks.
Transaction manager?
Yes. So for distributed transaction, it depends what implementation you want. So if you are looking for some two-phase commit implementations, there are already in Java, I think, the exit transactions and do those things. If you are looking for Sagas, I know there is this company called Eventuate. So do you know the guy Chris Richardson? He is a guy from microservices.io. So he has this company called Eventuate.io, and they have an implementation of Saga coordinator, and they call it the transaction manager and something like that. So if you are looking for those Saga implementation, you can go and find on their website. There is this GitHub repository. I don't know the name of the repository, but if you just search Eventuate.io Saga protocol implementation, so you can find the implementation of Saga coordinator. You cannot find the implementation for the shadows coordinator as such, because this is something which we are still in progress. You can find the entire store with all the components, but it's, as I said, that we are more like destructurizing it. So you can't find for the shadows, but for other two protocols, you can easily find. And later, if we manage to get these things out, maybe we will try to open source the coordinator or the manager for the shadows. Yeah.
I don't know if there is any project within the Apache portfolio that is doing this kind of solving this kind of problem. To be honest, JBoss had the driver as well, but I don't know if you meant for Giacchetta you meant a product by Apache. I'm not sure how to answer. There is a standard. You were talking about the implementation, right? Implementation under the Apache committee flag.
For instance, I would prefer standardization in Giacchetta.
Oh yeah, of course.
Being available for everyone.
Yeah.
Any implementator.
I don't know. It's a good question to ask around.
This would be big trouble for in-time work. So it would still be bigger without standardization process. If everyone builds his house,
Yeah.
the mechanism, then it will be lots of
Yeah, so I think, right, so I think what I understood is that, is there any standard protocol to handle the problem of distributed transactions, right? So there is no as such standard protocol, but from what I have read, so if you look at Spanner, if you look at CockroachDB and all these different databases, they solve the similar problems. So there is, I think this thing is a bit new right now because people recently, it's not, so for example, two-phase commit is very standard in databases. It's been there for years. So that's why the two-phase commit is also very standard, and there are a lot of implementation. You can find the tweaked implementation of two-phase commit, which are like faster than locking all and the entire tables. And there people are still trying to make it, I think, better and fast. So there are like some databases around to solve this problem, but in order to make those changes, you have to change your database, which is like very difficult or painful. So there is not very standard thing yet. Sagas is a bit standard. So if you just go on the Google and search for Sagas, you can find like hundreds of talks in different conferences, and there are some implementations around. So that is kind of going towards the standardization process. But I don't think there is a completely one way to do this yet. Yeah.
Thank you.
Thank you.